Lesson 16, friction. All right, so now we're going to be talking about the friction between two surfaces, right? So if you rub your hands together, that type of thing, so that's friction. Or mostly we're going to be talking about like pushing a box across the floor where the force of friction is the thing pulling back, right? But it's that spot right there, right between the box and the floor is where the friction's being created. So um, there are different theories of friction. You might think, well, it seems pretty simple. It's just stuff rubbing on itself. But once you start getting into, like quantum mechanics and how things actually interact, it gets a little bit more complicated than that. And in Physics 2030, we're just going to keep a more kind of simplistic view of things. It's not wrong. It's just a little, it's not telling the whole story. It's kind of, is it? Okay, so if you look at this picture here, what we're going to assume is that if you took every spot on this box, on like where it's in contact, you can think about it as that you have a whole bunch of like little normal forces, right? Pushing up everywhere where it's in contact. All those little normal forces all would add up to one giant normal force, this arrow, which is going to be equal to the force of gravity because it's not accelerating up and it's not accelerating down, right? They're balanced. So that's kind of what we're gonna go with. And for the most part, we don't even really need this idea. We just kind of need to know that there's a normal force pushing up and that there is some sort of force of friction that's going to be pulling backward when we drag this thing. But what we can say with normal force here, so if I think about, this normal force being one long arrow going up, that the bigger this normal force is, force normal, that's also going to make a big force of friction, which kind of makes sense, right? If you try to drag an anvil, it's going to have a lot bigger force of friction than if you try to drag a feather across the table, right? So we're saying really the bigger this arrow is, the bigger the force of friction arrow would be if you were pulling it. So that's one factor that affects friction. The other factor is something called the coefficient of friction. And I'm going to lead off with a joke for this one. So, all right. What do Greek cows say? Mu. You might not get it because this is the symbol we're going to use for coefficient of friction. It's the Greek letter and it's pronounced mu. It looks like a U, but it's pronounced mu. Um, Maybe that joke makes more sense now. So the coefficient of friction is what that's going to be called. And the way this works is that different surfaces have different coefficients of friction. So if you have sandpaper, it's going to have a high coefficient of friction. If you had, like ice, it's going to have a low coefficient of friction. So normal force and coefficient of friction are the two things that affect how big the friction force will be. So you can see if I look at my chart down here, like wood on wood has a coefficient of friction of 0.4. Wax wood on snow would be 0.14, and it goes down like that, right? All of these are going to be between 1 and 0. You're not going to have a negative coefficient of friction, and you're not going to have a coefficient of friction of like a million. They're always between 0 and 1. And you can see here too now that we have two types. There's something called the coefficient of static friction, and there's a coefficient of kinetic friction. So the word static, I don't know if you guys have done like static stretching in gym. Maybe that makes sense to you. Static stretching just means not moving. So the word static means not moving. The word kinetic means moving. So friction of moving, or sorry, friction of something not moving and friction of something moving. Um, so I'm going to turn my video or my camera around here so you can kind of see what I mean by these two. All right, so I'm going to be able to push this chair across the floor, right? And it has a certain amount of friction that's going to be holding it back, right? But there's two types of friction that are happening here. The first one, there's the coefficient of static friction, and what that is it's going to be the friction that it takes to get this thing even started moving. So you can tell that I'm pushing on this, right? I'm pushing this way on the chair, and I'm giving it a certain amount of force, and it's not even moving yet, right? But then once I get past a certain point, it'll start to move. It'll start to slide, right? So coefficient of static friction is that point before it moves. So when I'm pushing on it, pushing on it, pushing on it, and then and not moving. And then once it starts to move, now we're into the range of coefficient of kinetic friction. So it's the friction of the thing moving. Um, which one do you think would be higher? Well, the coefficient of static friction is going to be higher because if I'm pushing this thing, you've probably felt this before that, like if you're pushing like something across the floor or something, it takes a lot of force to get the thing moving. But then once you start it moving, it becomes a lot easier to keep it going, right? So static friction is before it moves. Kinetic friction is while it's moving. So you can see if we look back at our chart here that the coefficient of static friction is higher for every one, right? So it's 0.4 for that. Once you get it moving, it's a little bit easier. Okay. And that's pretty much what I just said over here. So the two factors, normal force and coefficient of friction, combine to give the following equation. So the force of friction is going to be equal to mu, the coefficient of friction, times the normal force. And remember what these little bars mean on the side? It just means the magnitude. We're talking about the magnitude of these things. And it has to be because we couldn't just multiply like with the vectors anymore because these are in different directions, right? The force of friction is going to be back and the normal force is going to be up. I can't multiply those as vectors because they're in totally different directions. Okay, so number one here says what friction force. Oh, sorry, and one more thing. I want to show you where these things are on your formula sheet. So, where's my formula sheet? Equation. There we go. Nope. All right, there we are. Okay, so we've done all of the equations in oh, no, sorry, we haven't done all of them in kinematics yet. There's some circular motion ones that are coming up. We've done 6 of those in kinematics. We've done this one now. Acceleration is equal to F net divided by m. And now we're in this one. Force of friction is equal to mu times Fn. So that's where we're at right now. Oop. Okay. So number one says what friction force must be overcome to start a 50 kilogram object sliding across a horizontal surface when the static coefficient of friction is 0.35. And this is important that it says static coefficient of friction, right? Because it says how much force must be, what friction force must be overcome, right? That's that we want to get over that point so we can like start it moving. That's talking about the static coefficient of friction. And it tells us what it is in the formula. So this one, if you drew a free body diagram, our Fg is equal to our Fn in magnitude. If you figured out what your Fg was, because it tells you 50 kilograms, and we know that things accelerate downward at negative 9.81, I can figure out what Fg is by going mass times negative 9.81, or just 9.81 in this case, because we're dealing with the magnitude. I'm going to get 490.5 newtons. I know this thing isn't accelerating into the ground or up into the air, so I know that the normal force is equal to that, right? So it's going to be the same. So now that I know the normal force, all we got to do is plug it into our new formula. The force of friction is equal to mu times the normal force, so it's going to be 0.35 times our normal force, which is 1.7 times 10 to the 2 newtons. So now example number 2 says a 400 newton object is pulled over a horizontal surface. If the coefficient of kinetic friction is 0.23 and the applied force is 120 newtons, what's its acceleration? So right off the bat though, it tells us that it's 400 newtons. Now what is that? Well, 400 newtons, that's talking about Fg. That's the force of gravity, right? So we just need to know that the force of gravity is going to be equal to the normal force. So normal force, done. We got that figured out. Now what we're going to do is figure out the coefficient, the frictional force. And that's pretty easy. All we got to do is multiply 400 times our coefficient of kinetic friction. So our force of friction is 92 newtons. Now what we just figured out is that this is 92 newtons. So remember, if we're talking about like what is this thing's acceleration, I need to have the net force. So that's going to be the difference between 120 and 92. And that's just what we did down here. So the net force is going to be equal to positive 28 newtons. So this thing's going to be accelerating this way, right? It's because it has a net force in the positive direction. Now what we got to do is just figure out what the acceleration of this thing will be. So we'd start off with this formula. Acceleration is equal to F net divided by m. But we hadn't figured out m yet. But m's going to be pretty easy to figure out. We know that force is equal to mass times gravity. If you rearrange that, the force of gravity is 400 newtons, acceleration is 9.81, and our mass is going to be 40.77 kilograms. Okay, now that we know that, we can figure out the acceleration using our net force that we figured out now. So if you plug that in, we get 0.69 meters per second squared. Okay, number 3, a 10 kilogram box is dragged over a horizontal surface by a force of 40 newtons. If the box moves with a constant speed, big word there, constant speed, of 0.5 meters per second, what is the coefficient? Oh, sorry, hope you guys could hear me. I forgot I just had my mic pointed the other direction. What is the coefficient of kinetic friction for the surface? So if we draw our free body diagram like this, everything should be balanced, right? Up and down and left and right, because it's moving at a constant speed. Our thing isn't accelerating. It's at a constant speed. So up and down, these things are balanced. So I can say Fn is equal to Fg, and I know that mass times gravity is Fg. So if I multiply those, I get a normal force of 98.1 newtons. So we got that. Now here's kind of the new thing. Left and right here, if we look at that direction, the net force is going to be equal to Fa plus Ff, right? So you could say that. And then what I'm going to be able to do is say, okay, well, F net is equal to 0, right? So force of friction is going to be equal to negative 40 newtons. The other way of thinking about that is that you could just say, okay, well, Fa was equal to 40 newtons. Well, if that's equal to 40 newtons, then, and I know that these are balanced, then I know this is going to be negative 40 newtons. So this formula was just a different way of saying the same thing. So however you want to get there. Okay, so we know that now. Now we just need to use our new formula rearranged. So we can say mu is equal to the force of friction over the normal force. Plug in your numbers and you get 0.41. Notice that the coefficient of friction is unitless because I went newtons over newtons. Newtons over newtons would cancel. I don't have units at all for coefficient of friction. It's really just a ratio, right? It's a ratio of the force of friction divided by the normal force. So ratios don't have units. All right, example 4. I'm going to let you guys look through that one and see if you can make sense of it on your own, because I'm going to go through one similar to this in the practice problems. So I'm going to end that video there.